Welcome to installment 7 of writing a 6502 assembler in assembly language. Last time I started on the scanner, which reads the input file character by character and builds tokens. Those tokens will be then input to the parser, which will look for syntactically valid statements and generate object code from those syntactically valid statements. Today I want to continue working on the scanner. In particular, I want to work on getting these literals. That would be the character literal, string literal, decimal, and hexadecimal literals done. Actually, 3 of those things are basically the same thing. The character literal, the hexadecimal literal, the decimal literal, and the character literal will all produce a 16-byte value, a number. A 16-bit value. Sorry, not 16-byte value, a 16-bit value. Okay? Or actually, I should say they will produce a value, that a number, a numeric value, which will have a size associated with it. And that size will depend on what you gave it. So for example, a character literal will come back as an 8-bit 1-byte value. A hexadecimal literal will be 1 byte if it is 2 hexadecimal digits or less, and it will be 2 bytes if it is more than 2 hexadecimal digits. And a decimal literal will be 1 byte if it can fit into 1 byte. That is, the value is from 0 to 255. And it will be 2 bytes if it is greater than 255. Now this doesn't account for negative numbers, but negative numbers will come later because they will actually look to the parser like a minus sign in front of a positive number. And therefore, when the parser sees that, it will have to say, aha, if this is like minus 240, the scanner is telling me that this is a 1 byte decimal number, but I need to change it into a 2 byte decimal number because it's now a negative number, and minus 240 doesn't fit into 1 byte. So that will happen later. So for the time being, these numbers are considered to be unsigned numbers. Okay? And if you remember, I think I'll start with get decimal up here where we do this. Okay, I'm checking to make sure that I've got a character between 0 and 9. And then I unget that character and then go to get decimal. That means that here in get decimal, right here, we know that the first character we read when we call get C is going to be a valid decimal digit. So we don't have to worry about it at all. What we will need here is we'll need a token value. Well, and notice we're going to need another little variable here. I'll call it token value, tokeval. This is a 2-byte value. And let's go ahead and get toke size. This is a 1-byte variable. This will be, either 1 or 2, depending on how many bytes it is. And so what we'll do here at getDec, we'll just go straight to get a character. Or should we do that? Okay, well, let's talk about how this get decimal works. How get decimal works is it's going to, every time it gets a valid decimal digit, it's going to multiply this toke value by 10 and then add in the value of the digit it just got. So actually, I suppose the first thing we ought to do is make sure this toke file starts out at 0. Okay, and then right, we only want to multiply it by 10 if we get a valid decimal digit, which we know the first one will be a valid decimal digit. but I'm thinking, let's just go ahead and get the character first. Get a character. All right, we need to go ahead and compare to see if this is indeed a valid decimal digit. So get dec 9 is going to mean we're leaving. It's not a valid decimal digit. So if it's less than an ASCII 0, we're going to bail out. If it is greater than an ASCII 9, we're also going to bail out. We're done. At this point, we know we have a valid decimal digit. So at this point, we need to multiply this thing by 10, Tocqueville, and then add this character. So notice that at this point, we know if we're comparing the character that we just read from the file to ASCII 9 plus 1, and if it's less than that, it means it's an actual, I'm sorry, this should be greater than or equal to that, we leave. Otherwise, here we have a good character, a good decimal digit, and carry is clear. So what we can just do is go ahead and subtract 0 from it. But because carry is clear, we're going to subtract 0 and then subtract 1 more. Because when carry is clear, that acts like a borrow to subtract. So it's going to subtract the 0 plus 1 more. So we need to subtract not the ASCII for 0, we need to subtract the ASCII value for 0 minus 1. Okay, so in this case, for example, if we have a 0, it will subtract 0 minus 1 from our 0, giving us 1, and then it will subtract another 1 because carry is clear. So we'll get 0. And that works the same for all. So we're changing the ASCII character 0 into an actual 0. That's the point of what we're doing here. And we're changing an ASCII character 9 to an actual number 9, and so on. And now that I've done that, I'm just going to push that in the stack for a moment, because we need to multiply this by 10. Okay? The 6502 does not have a multiply instruction. So we have to multiply it, by hand, so to speak. And multiplying by 10 is a matter of shifting it up to the left, shifting it to the left 1 time, which multiplies it times 2. Remember that value, then shift it up 2 more times, which then is a total multiplication of 8, and then add that value we just remembered, the shifted up by 1 version. Okay, so we basically multiply by 2, multiply by 8, and add those things together. That will be a multiplication by 10. Okay, so let's we'll shift Tocqueville left, the low byte, left by 1. And when that happens, what happens, let me pull up this thing again. Okay, when we shift that byte left by 1, then the high bit goes into the carry flag. So we can then get that high bit into the high byte of Tocqueville plus, that is Tocqueville plus 1, by doing ROL, right? So the low byte, we're shifting the low byte left. That puts a 0 in here and puts the high bit goes out into the carry flag. Then we do ROL, which puts the carry bit, which is coming from the high bit of the low byte, into the low bit of the high byte. That sounds like a tongue twister. And then the high bit of the high byte goes out into carry, but we don't care about that. We're just going to ignore it. It's disappearing. Okay, we multiply that by 10. That multiplies this by 2. All right, now we need to remember this somewhere. So I'm just going to go ahead and load it into X and Y. You know, I've written this type of code many times before, and I've probably done it slightly differently every time I've done it. That's just kind of how it is. All right, now I've remembered that multiplied times 2 version here. After this, it's multiplied by 4. And one more time. Now it's multiplied by 8. Now I need to add this multiplied by 2 version, which is in X and Y, to this thing here. And I don't know for sure that the carry is clear because this rotate could have put a bit out on there. So I have to clear the carry. I'll transfer the low byte of the multiplied by 2 version into A and add it to Tocqueville and store the result in Tocqueville. Okay, and then I will move the high byte of the multiplied by 2 version, add the multiplied by 8 version, and store that, sorry, this is +1, and store that there. So now I have multiplied Tocqueville by 10, and it took this many instructions. I could do it slightly faster. I could, you know, have a loop here, but that would just be a loop for 2 things. It would save, maybe it would save a byte or 2. Yeah, I'm sure it's possible to do it faster, but for me, correct and like if I can write the code fast rather than having to think about how to do it, saving a few bytes or cycles, that's what I'd rather do. Okay, so now I've multiplied this by 10. Now I'm going to get the value of the digit off the stack and add this in to Tocqueville as well. Again, +1. Okay. Now this brings up in my mind, you know, at this point when I'm adding these things together, whether I could go ahead and add in this thing I pushed into the stack here as well. Let's see, theoretically it's possible that these things could be, I just have to think about the case about, for example, could these be such a large number when I added this and this together? I'm sorry, when I added that what was in X, that is the ×2 version of Tocqueville and the ×8 version of Tocqueville, the low bytes. If I added those together, could it be large enough that if I added this value as well, which goes from 0 to 9, that I somehow like get a carry of more than 1. I think I'll just I'll think about that later. It really depends upon what are the actual possibilities for these things. What numbers could possibly be in X, what numbers could possibly be in Tocqueville, in the low byte of Tocqueville. My impression is probably it would be fine. I could go ahead and add in, I could go ahead and do pull A and add that here, like right here. I feel like that probably is okay, but I'm not 100% certain. So I'm not going to do it now. It just saves a few instructions. So anyway, I multiplied by 10. Right there. And here I add in the digit value. Okay, after I've done that, I'm ready to go up and get another character. So go up to get dex 0. get dec 0. Okay? So I've gotten a character. It's a valid digit. Okay? And so I find the value of the digit by doing this subtraction here. I save it on the stack temporarily. I multiply the token value by 10. I add in the digit value. And then I go back to get dec 0, which is up here. Okay? And if I find something which is not a decimal digit, I branch to get dec 9, which is here. And now I don't think this is too far, but if it happens to be, then I can rearrange it quite easily. Okay. What I want to do here now is load. My token is just going to be a number, right? It happens to be decimal here, but once we've turned it into a binary number, which is what we're doing here, we don't care. It's just a number. And return that. Oh, I am quite dumb. I forgot. I first have to put back the character I got, which was not. Right up here, I get a character. I compare it to see if it's less than an ASCII 0, I go down to the bottom, I'm done. If it's greater than or equal to, or if it's greater than ASCII 9, I go down to the bottom, I'm done. Which means the first thing I have to do is put that thing back, because this is some character or byte that comes after the decimal literal. I mean, it could be a space, but I just need to put it back. And I'll say, okay, I have a number. That's my token as a number. And I'll return that. So when the parser calls this scanner, it's going to say, aha, I got a number. And then it will have to look in the variable tokeval to see what the value of the number is. Okay. Now I also was going to deal with the token size, right? And now that I'm thinking about it, I guess I don't really need to bother with that at the moment, because the parser can itself look and see that the high byte of tokeval is 0 or not. So it knows itself, the parser already knows whether it's what the situation is there. So let me just delete this for now. I might bring it back later, but for now I'm going to delete it. Okay, good. Okay, let's just do the same thing with get hex. Now, if you remember last time I had this thing where I did all this checking to see whether or not it's a good hex character, a good hexadecimal digit, before I ever call get hex, because I wanted to enter knowing that I have a good hexadecimal literal. But the downside of that is I have to repeat all this stuff. Like, I have to repeat all of this code here, down there in the get hex subroutine. So I'm just thinking, the alternate is to not do this. Just as soon as I see I've got a $sign, I jump to get hex right here. Then what I'll have to do is, down here, I'll have to say, aha, I'll have to know that this is the first time I'm getting a character, and say, if it's not a hexadecimal digit, now there's a problem, because you put a $sign, which is supposed to mean there's a hexadecimal digit, a hexadecimal number coming, and you didn't give me one. It would save doing all that checking above the first time. Well, for the time being, let me just go grab this code. All right. Okay. No, not delete it for now. Might delete it later, but not for now. Okay. All right, so I'm going to, inside the get hex subroutine now, I'm going to get a character and see if it is actually a hexadecimal digit. Okay, so the thing is that if it's the first time I'm getting a character in this routine, then if it's not a hexadecimal digit, it's an error. Because all I've seen so far is the $sign. If it's not the first time, if I see something which is not a hexadecimal digit, but I've already gotten some hexadecimal digits, even if it's only 0, then it's fine. And I wouldn't want to return an error. It's just the end of the hexadecimal literal. That's why it's kind of, I'm still not sure exactly how I would like to do it. If I don't want to repeat all this code up top, then instead I would have to come in here with some flag set that would tell me this is the first time. Yeah, this is the first time. Okay, I think I know how I will do that. Yeah. And as usual, it will just be self-modifying code. Let's get rid of that. Okay, so get a character. And I'm going to see if it's a good character or a bad character. Okay. Now, I want to change this now. It's not bad hex, but let's just change it to not hex. How about that? Is hex. Not hex. Is hex. Not hex. Is hex. All right, so now not hex. Now I'm going to load some random byte. If this byte is get rid of that. Oops. Okay. If this byte is, this is my flag right here. I'm not actually loading a 0 here. This is the first digit flag. So first digit flag is set. Okay. So I'll say if it is not a 0, then go to bad hex. And that's an error. Okay. If it is 0, oh, and by the way, no. Okay, if it is 0, then it's not the first hex digit. So it's not a bad hex, and we just have to do the same thing we did here when we finish, which is unget the character, which is not a part of our numeric literal, and load tnum and return. Return the tnum token number. All right, so, oh, but I don't want to do an A because A has my character. Let's do an X. All right, A has the character. So if I did load A here, I would blow away this character, which is not a hexadecimal digit. Okay, so JSR ungetsy to put back the character which is not a hexadecimal digit, and then return token number. All right, so now we go down here to isHex. That means that we saw a real hexadecimal digit. All right. And actually, I don't want to jump to isHex. This one right here is saying what we saw was a digit from 0 to 9. Okay? And that's a decimal digit. This is a capital A through F. So this is ABC digit. And this is a lowercase a through F. This is also ABC digit. Okay. So here we have ABC digit. And what I want to do here first off is I want to change. I need to look up my ASCII table again. Okay, and I see that capital A is hex 41. Lowercase a is hex C1. So what I can do is I can get rid of that byte, which is the 20 byte. So basically, this 2 here, this bit here, which is set to make this 2, is the thing that makes it a lowercase letter. If this bit is cleared, then it's an uppercase letter. And I can clear it by ANDing the inverse of this thing here, right? So, or the bitwise complement of this thing here, which would be, 2 is 0, 0, 1, 0, so it would be 1, 1, 0, 1, which is a D, and then F. Okay, so that will clear that bit. So at this point at ABC digit, we've gotten, for example, a lowercase a will be turned into an uppercase A. Hang on a second. Actually, A is at 41 hexadecimal, capital A is at hexadecimal 41, lowercase a is at hexadecimal 61, and 0 is at hexadecimal 30. Okay. So that changes the lowercase digit to a lowercase letter to an uppercase letter. Let me go down to the decdig here. This is basically the exact same thing we have in the down here, right? But here we had the case that carries clear is to subtract 0 with 1, 0 minus 1. Here also we go to decdig carries clear, so we have to subtract ASCII 0 minus 1. It will actually subtract this plus subtract another 1, so that means it will subtract ASCII 0. And again, I'm just going to push that for the moment. Okay, so we have the situation here. If we go to, when we go to ABC dig, then the carry is clear, and this won't affect the carry. So that means we will have changed we'll have, for example, hex 41 And hex 41 is actually, well, in decimal numbers, uppercase A is 65 and a 0 is 48. The difference between those two is 17. Okay, so if we subtracted 17 from an uppercase A, we would make it a 0, an ASCII 0. And then if we subtracted this ASCII 0 here, we would make it a 0, the number 0. But we actually want the uppercase A to be a 10, so we subtract 7 from it. So we should subtract 7. But carry is clear when we come down here, as you see. So we actually subtract 6. And then it will also subtract, it will actually subtract 7 because carry is clear. So subtract 6 plus a borrow. So it'll subtract 7. So for example, if I have a lowercase a is hexadecimal 61. This here will change hexadecimal 61 to hexadecimal 41. That'll make it an uppercase A, which is decimal 65. This will subtract 7 from it because it'll subtract this 6 plus the borrow. So that would be 65 minus 7, which will be 58. And then this will subtract the value of ASCII 0 from it, which is 48 in decimal. So 58 minus 40 is 10. So that A will turn into a 10, and that's exactly what we want. Okay, so we're going to push that just for a moment. Now we have to multiply Tocqueville by 16, not by 10, as we did for the get deck. And that's just a matter of shifting. So we can ASL Tocqueville, ROL Tocqueville plus 1, and do this 4 times. Okay, do this 4 times. I think it's this, in this case, we'll just use a loop. So put a 4 here. All right, decrement X. If it's not 0, then go back to get hex, I'll just call it get hex 1. Okay, so load X with 4. Okay, shift the whole thing left by 1, decrement X. If it's not 0, so we'll do it for 4, 3, 2, 1. That'd be 4 shifts to the left. Okay, get the value of the digit back in here. Again, just like last time, we can't be guaranteed that the carry is clear or set. We're basically in exactly the same position right here, where we want to add this in. Okay. This is plus 1. Okay, so we've added in that. Okay, here we've shifted the Tocqueville value 4 times to the left, which is multiply times 16. And then we've added in the value of the new hex digit. And now the thing is that if we've gotten at least one valid hex digit, we need to make sure that this thing right here is 0, right? This has to be 0. And it happens to be the case that we have, after this here, when we exit this loop, X is 0. So we'll just go ahead and store that right now. N, not hex. plus 1. That's our flag, right? And maybe we shouldn't call this not hex. We should call it, you know, first flag. Okay, first flag. That means these have to be also first flag because that's where it is. Okay. So as long as this, what loads here is really a 0, then that will say, fine, it's the end of our hexadecimal literal, and we exit. If this is in fact a 1 or something which is not a 0, and we get something which is not a hex digit, then we will say, oh, that's an error. So if we get a valid hex digit, which we know we have done by here, we go ahead and take this value of x, which is now 0, and store it there to make sure it's 0. And then after adding the value of the hex digit into our token value, we have to go back up and get another character, so we'll go back up to get hex. So jump get hex. And now what we need to do is make sure when we call this above that we set this to something that's not 0. Okay, so actually we're not going to do all of this stuff here. Okay, and we're not going to check for a good hexadecimal digit. Instead, okay, we get a $sign. If it's not a $sign, we go to scan 5. Otherwise, we can just store that $sign in first flag. It doesn't hurt, it's not 0, it'll work. And we jump to get hex. Okay, that looks good. Now we get to delete a bunch of stuff. Okay, right. So now back in the main scan routine, we see if we get a $sign. If we do, if we don't, we go ahead and keep checking to see if it's a decimal number or whatever. If we do, we store that $sign in first flag down below, and it doesn't matter what we store there. It just has to be something which is not 0, and a $sign is not 0. And then we jump to get hex. All right, so we go down to get hex. Here we go. We get a character, and assuming that it's not, for whatever reason, a hex digit, we'll branch to first flag. And we'll load this thing here, this byte. Oh, it needs to be stored in first flag plus 1. Let's just make sure I don't screw that up. Right, not in first flag. I'm just writing over the opcode then. We're going to store it in first flag plus 1. Okay. So it will end up loading a $sign here, which is bad. It's not equal to 0. It goes to bad hex, error. But if we do get a good hex digit, then we'll go down here either to dec dig or abc dig. Here or here. Okay. We'll shift up the token value 4 places to the left, which multiplies by 16. And then we'll store 0 in not hex, but in first flag plus 1. Right here. Okay, we'll store 0 there. We'll go ahead and finish building our token value. Jump up to get hex. And suppose it's just $0, and after that there's no other hex digits. It'll say, okay, it's not a hex digit, it's a space. So for example, it's a space, will be less than 0. It'll go down here. Load X. Oh, it's a 0 now. That means we just unget the character we read and we return tnum. We're good. Okay. So that's code for the decimal and hexadecimal literals. Okay, let's keep going. And now I am interested in the character literal, which is down here. Now, when we enter this, we've already seen the first single quote. And if I remember correctly, the single quote, you know, I should look at my cheat sheet of the editor here and see how do we page up and down, scroll up one page, scroll down one page. I see, I have to do it like this. Okay. All right, there we go. All right, here we go. 39 is the single quote. Okay. So we've already seen a single quote character. And really all we need to do here is go ahead and get another character. We need to make sure it's not a backslash, because if we look at the documentation somewhere here, yes, we'll see that we can use C-style escape sequences in our character literals or our string statements. Okay. And so I need to look for these. So we have all these possibilities here. So we compare this to a backslash. And first we'll worry about if it's not a backslash. All right. If it's not a backslash, then it's the character, whatever it is the character we're going to return in the string literal unless there's some problem. So we'll remember out in the stack for just a moment. Okay, we're going to JSR get C, and we're just going to make sure we get another single quote here, because that's what's required. If I look at the documentation, does it talk about expression statements, about character literals? It's actually an expression statement, but maybe I did not explicitly write here about character literals. But in any case, the idea is that they can only one character can be inside a character literal. C allows for more. I'm not going to fool with that. One character is in a character literal. Okay, so if we, here, when we enter, we've already gotten a single quote. We get another character. It's not a backslash, so we're just going to push it onto the stack and now get another character just to make sure it's a single quote. Okay, if it is a single quote, then we're going to return a number as our token. Okay, that's fine. No, not yet. Actually, what we need to do first is get that character that's going to be there back, store that in Tokefile, store 0 in the high byte, load tnum, and return. So we're returning a number where the high byte is 0 and the low byte is whatever character or whatever ASCII value of the character that was in the character literal. Okay. Now, at this point, this is where we got a character, but then we did not get a single quote like we expected. So this is going to be an error situation. Yeah, it's an error situation, so I'm thinking we'll just throw this character away, the one we pushed into the stack, but you're going to throw that away. Why we pulling it off means we're going to throw it away because it's going to get wiped out soon. And we're going to get the what can I call it? Lit error. CC, character constant error. Good enough. Jump error. All right. And bad character constant. If I can spell, it would be nice. Okay, bad character constant. All right, here's the situation where we get a backslash, which precedes one of these escape sequences, one of these things here. Okay, and what I'm going to do here now is I'm going to JSR to get escape. All right, and I'll just go ahead and put that code right here. So get escape is going to JSR. Okay, and now what we're going to do is have an escape tab. Okay, that has all these things in it. Okay, so ntr0, I can do like this, 0 ntr. Yes, they have to be lowercase. That's just my decision. All right. And what we'll do is, you see how slash slash turns into a slash, slash double quote is a double quote, slash single quote is a single quote. What we should, it's very easy if I map these out, but the rest, if you have a slash followed by anything, it just returns that anything. Right? So that slash x would return x. Right? Slash @ returns @. Because my other option is to throw an error and say, I don't understand this escape sequence. You know, but why not I just not bother with that? Instead, I'll do it like this, okay? So these are the things that I have a possibility. I want to point out, this is an ASCII 0 right here, which is the decimal value 48, right? Whereas this is a binary 0. 0. These are not the same thing. So what I think I'll do, though, is do like this. Now I need to what an oh, it's going to return. That's going to be OA. Oh, so A. Actually, let's put a T here. That's returning a 9. Okay. N will be A, R. It is hex 13, which is hex D. Okay, so what I have here is I have an ASCII 0 maps to a binary 0. and ASCII T maps to a binary 9, which is a tab character, and ASCII N maps to a binary hexadecimal A, which is a new line character, and ASCII R maps to hexadecimal D, which is a carriage return character, and then this means there's nothing left in the table. Okay, so we get the character, and let's just go ahead and, oh, I just thought of something. Every time I get characters here, I probably need to check, well, there's a problem going back to the get character. Remember how when I was making the get character routine, I eventually made it so that I returned a character in X and Y. And so first off, I'm assuming that it's returned in A the whole time, but it's not actually. And also the reason I was returning X and Y was because I was using it as a 2-byte return value that allowed me to return FFFF, that is -1, for end of file. And I'm not checking for that anywhere. So I think actually I'm going to have to rework this a little bit, but I won't do it now. I think probably, well, first off, like when I unget a character, I'm just ungetting a single byte, and that's no good because I have to, if get C is returning a 2-byte value, I need to unget 2 bytes. So yeah, there's an issue here. I'll have to look at that next time. See, these things just come up. I forgot what I was doing and forgot how I did things, and now I'm going the whole time assuming that getC returns a character in A. Okay. I mean, I could say that if you try to use load into this assembler a source file which has, you know, bytes with the high bit set, that is, that they're not actually ASCII, then basically you're just in big trouble. But actually, a lot of Apple II files have the high bit set, so probably instead I should just, you know, clear the high bit. I'm sorry, have the high bit set. I should clear the high bit of any byte read from a file that's assumed to be a source file. It's a good question, and then I have no way to return, like, you know, you could have weird control characters stuff in a file. Yeah, sure, it's an error, but you could have it, possibly a delete character, for example. So I couldn't use that as an indication of end of file. I might have to do something else. But for now, I'm just going to keep assuming that I'm returning the character in A for the time being. Next time I'll think about it before next time, and next time I'll go through and try to work it out. So anyway, JSR getC. Let me just push that. Okay. And what did I call this? ESCTab. Okay. If it's 0, then go out. Just get ESC9. So this will happen. It will load a 0 here when the X register is pointing here. Okay. And then compare. And now this is, instead of pushing this, I'm going to make this get C0 plus 1. Not that. Just get C0, okay? So I get a character. This is the character after the backslash. I store it here. Okay, I load x with 0. I get the first character from the escape tab. If it's, well, I get the next character from the escape tab, but ultimately it's the first character. Here, get ESC0. One. Okay. This is getting the, if it's equal, then I'm done. If it's equal to 0, I'm done. Otherwise, I compare it with the character that I got here. Okay. If it's not equal, and actually, I think here I should just go ahead and increment x. Okay. Now I compare the character from the escape tab with the character I got from the file. Okay. If it is equal, then I go to get ESC8. And get ESC8 is going to load escape tab x. See, I just incremented it. So it's going to get a character from escape tab. If that's 0, it's done. Otherwise, it's going to increment x and then compare the character from the escape tab with the character that came from the file, the source file. If they're equal, go to get ESC8, and it's incremented x here. So now it will load the character after that. It'll load the byte after the one that matched. So for example, if a T matched, it'll load this one here. It'll load this 9. And it will return that. I'm sorry, here we are. Okay, it's just going to return that there. It's returned the mapping. Okay, and here, this situation here is when it has loaded, it's gotten a 0 here. It's gone to the end of the table, the escape table, and it goes down here. So what it has to do in that point is it has to retrieve this character here and return that, because that means it didn't match anything. It's like /q. It's just going to return q. Okay, so it's just going to retrieve this and return it right there. Okay, the situation here is if it hasn't matched. So now it's going to increment x again, because after incrementing x here, x is indexing one of the mappings. It's indexing, like, if this is loading a T, then after incrementing x, x is looking at the 9, the ASCII 9. I mean, T represents 9. Okay, if that doesn't match, it's not a T. We need to increment x again to get past that 9 to the next character, which could be a valid character. And we go back up to get esc0. All right. Okay, so we come here having seen a backslash. We get the character after the backslash, store it here. Load x0, so we're starting at the beginning of the escape tab. Load a byte from the escape tab. If it's 0, then we've looked at the whole escape tab, we're done. So we get this character back, right, which is the one after the slash, and we just return it. It didn't match any of the things in the escape table. We would just return that character. So if you type in /q, you return a q. //, you return /. Double quote, you return double quote, and so on. Okay, if when we get this character from the escape tab, it's not a 0, then we increment x. Now x is indexing the mapping for whatever this thing is. we compare whatever this thing is to the character from the file. If they're equal, we go down here, we load the mapping and return it. If they're not equal, we increment x to get to the next byte in the escape tab, and then go back up here to keep checking. That looks good to me. Okay, and once we've done that, the get chur literal subroutine is complete. Okay, get string literal also use this exact same get esc subroutine here because it needs to deal with those exact same / escape sequences. But this will be a little bit more tricky because we have to use someplace to store the string, and what we'll probably use is we will use address 200, which is from 200 to 2FF in the Apple II is a buffer, an input buffer, and it's available to us. I mean, if you're not running an Apple II, if this code is running somewhere else, then we'll have to have some other buffer. We just need 256 bytes where we can store the string data, and we're not going to allow strings greater than 256 bytes, so we don't have to worry about that. If it's more than 256, that's too bad. Okay, and like I said, we have to deal with this issue of getC, where I've basically screwed up because I wrote getC to return a value in x and y, and then I'm pretending like it's in A the whole time, and I'm not checking for it into file. So next time what I will do is probably first fix that problem, and then get the string literal working, or at least write the string literal code, and after that, I'll be ready to write the get name code. Now that's going to be kind of large and complicated, but at least I can write the code to just like read in the name, and then without worrying about if it's a symbol, without checking to see if it's a reserved word or an opcode or a pseudo-op or anything like that, just read it in and say, okay, it's a name. And once we've done that, I will be in the position to actually test this code, like, try to read in a file and see if I get good tokens out. So that's what will be coming up next time. And until then,